Release 2.19.86 of KretSim contains support for a programmable component, some other new components, a memory cell injection feature, a warning log, a show drive status feature, some new capabilities of the test sequence editor and signal analyzer, and some new command line options. Let's start with the PLD component. It is the old and famous GAL22V10 from Lattice Semiconductor. However, here it is in its more recent incarnation, an Atmel ATF22V10C. They are pretty much compatible with each other. One can edit the logic equations of this device by using this window. The only supported device is the GAL22V10 at this time. Here is the place for some general text about the program that you for some reason don't want as comments in the source code. And down here you write the program of the device. The chosen language is GAL-ASM. First you declare the input and output pins. These correspond to the physical pins of the device from pin 1 to pin 24. Ground and VCC can't be changed. The inputs are found on the first row, plus this pin on the next. The rest are outputs. NC means not connected. Below the pin declaration, you have the equations. The syntax is simple. The output is expressed as a combination of inputs and outputs. An output pin may be in logic mode or in register mode. In logic mode, the pins react immediately to the changing inputs, while in register mode, it is only set during a positive clock flank. All registered outputs share the same clock, which is pin number 1. I cannot go into the details of this, but you have a help button here that shows you the most important features. Let's say that we want to implement a NAND function. We declare two inputs, I1 and I2, and one output called NAND. The equation is then specified as NAND is not I1 and I2. Limitations in parallelism prevents us from using parentheses or having the inverting on the right-hand side. So we need to have the invert sign on the output. Hit apply and the new pins appear on the device. It is possible to put the invert sign on the pin declaration instead of in the equation. That uses a different inverter in the circuit, but the result is the same. KretSim interprets the inverted outputs as being active low and therefore adds an overline to the pin name. But enough about writing equations. By using these two buttons, you can import or export a PLD file, and this button helps you produce a JEDEC file or even to program the device. KretSim only supports the Mini Pro programmer, but if you have one of those, you can pop an ATF22V10 device into it and hit Flash Device and it will program it for you. It automatically exports the PLD file and then converts it to a JEDEC file, and finally it programs the device. It issues a verification error, but the device works fine anyway. If you have some other programmer, you will have to use the JEDEC file. If your programmer doesn't support JEDEC, you will have to convert the JEDEC or PLD file into an appropriate format for your programmer and flash it outside KretSim. KretSim comes with binaries for an open source implementation of GAL-ASM called Galette and Mini Pro software. Galette produces some other nice files besides the JEDEC, for instance the chip file, which shows the pin layout of the device. It is also possible to inspect the internals of the device. Here you can see the inputs, the asynchronous reset and the synchronous preset. Each column in this table represents one output, where the first row shows the logic expression, the second the register value, which is only valid for registered output, and then the tri-state pin and the value of the output pin. Let's have a look at some other news. We have some other new but less complex components, pull up and pull down components. Note that these have a limited timing characteristic. Be aware that they may act very slowly in one of the two directions in real life. In the simulator, they are instantaneous in both directions, so use them with care. We also have a step component. This can be used to simulate, for instance, a power on reset. And third component is the generic time delay. It works exactly as expected. Another new feature is that the memories now have an additional parameter called cells. It is used to inject values into memory cells of the component. If I want memory cell 100 to contain FF, I just write 100:FF. I can add additional cells by a semicolon, for instance 101 with hex 17. These are all assumed to be hexadecimal values. If we inspect the memory, we can now see that these values are in memory. This is, however, not the most valuable use of this mechanism. Its power shows when we write a test sequence. If we open the test editor, we can use the component parameter override to specify that some cells should be set to specific values for that test sequence. Select the memory component, choose the cells parameter, and say that cell 102 should contain 77. That does not appear in memory until we run the test sequence. Please note the distinction between these two different places to specify memory cells. The parameters will be saved as a part of the circuit specification and will be a part of the circuit file. When we're using the component override, that is a part of the test specification and will not be saved with its circuit, but with the test vector file. We can see this by saving the test sequence and use this new edit button to see the test sequence file and its overrides. Here it is worth noting a maybe peculiar behavior that some may consider a bug. It is possible to save the circuit during simulation, and that works just fine in most cases. One may want to refrain from doing that anyway, unless you know what you are doing, because at the start of the simulation, the components are injected with the parameters from the test sequence and are removed as soon as the simulation is stopped. So if the circuit is saved during simulation, these temporary parameters will be saved with the circuit, and that may not be what you want. That mechanism may be handy for some types of debugging, but I would say that in 95% of the use cases, that's probably unintentional and will cause confusion. So don't save the circuit during simulation unless you really know what you are doing. This feature is likely to disappear in some future release. If one specifies illegal values, for instance outside the memory range, a new window shows up, the log window. It displays information, warnings, and errors. For instance, if one specifies to load a file, it can tell you that 41 bytes were loaded from that specific file, or give an error if it cannot find that file. There are also some news for pinpointing odd behaviors. If we study a more complex circuit and run a simulation, and want to understand why the address bus is 300 here at 2 microseconds, despite that the CPU is obviously not driving the data bus. One can get some help by using the nets window. Here we find the address bus A. To the right we see a list of connected ports. However, after looking for it for a short while, we realize that it doesn't explain why the bus is 300. These three and this one are inputs and not driving the circuit. And the only driver we can see, the CPU address bus, is in tri-state. The reason is that this is the local net only. And if we actually look closely at the list, we see that these are actually not inputs but in-outs. That means that they are connected to other nets outside this circuit, or inside components perhaps. To see these nets and their ports, click the checkbox Show Connected Nets. Now that was a bit overwhelming. To find the cause, we're only interested in the ports that actually affect the value of the bus, not the inputs, nor the in-outs. We only want to see the actual drivers, so tick this box. That's a much shorter list, even if it's a little bit strange. The easy bit is to see that the CPU address bus is still depicted as tri-state. For the other ports, we see that they are not local for this sub-circuit. The double colon indicates that they have an absolute path from the root circuit. The circuits are APB high and APB low. Let's go there. Here we can see that the outputs from C1, Q0 through Q7 are driving the address port through the splice component. This splice component is the reason why these outputs are reported as individual pins or bits rather than a bus. There is a shorthand for doing this. Right-click the net and select Show Drive Status. Then it automatically selects the net and ticks the two boxes. One can also note that these paths are local and the other ones are still absolute. Let's go back to the test sequence editor. The layout and editing is now a little bit more Excel-like when it comes to F2, return, home and end keys. There are also new context menus for the cells and for the top header. Go to time means that the currently displayed time of the simulator is set to the input time of this particular test vector. So here we can jump to 8.4 microseconds. One can also use the shortcut T. Normally KretSim keeps track of renamed ports, nets and components and updates the test editor and signal analyzer with the new port or component name. However, if you have several test cases for one circuit, this synchronization is only possible for the currently loaded circuit and test file. So, if you have a new test sequence loaded that has the wrong name of some port in the test sequence editor, then the simulation won't run. In that case, you can tell the editor by using this reassign that please use this port instead. That saves you from inserting a new column, copying over the contents of the old and delete the old. It is also possible to use a regular text editor to edit the test sequence by hand, as you saw previously. You can use reload after you have saved it. You may configure which editor to use by using the preferences. This button is a shorthand to add all the inputs and outputs of this test sequence into the signal analyzer. Both the signal analyzer and the test editor has a live checkbox. If these are checked, the progress of the simulation is visible in each window. The drawback is that the simulation slows down when these are checked. There are just a few changes to the signal analyzer. You can now enter the min and max of the visible range and use the middle button to set the currently visualized time. The command line version of KretSim has a few new options. -X is for printing outputs in hex format, and this works just as the test editor checkbox. The command line tool has a feature that doesn't exist in the GUI tool, which is a simple circuit analysis that warns about, for instance, unconnected inputs. -Q disables the printout of those warnings. When KretSim is run only with a circuit and a test sequence file, the simulation is run and a trace log is printed, but there is no verification. One uses -V to enable this verification. However, note that -V suppresses the printed signal trace and -P overrides that. As a side note, the command line tool is a bit faster than the GUI tool, which makes it even more suitable for batch execution of large sets of tests than the GUI tool. In fact, batch execution isn't supported by the GUI tool at all. Well, that sums up all the changes in this version. Happy simulations!